the tutorial, this week we will have three problems. The first one, we have a bronze ball of mass m naught is dropped on the mass of a SDF system from a height h, as shown in figure. Here you can see we release this mass m naught from this height h, and we will have one impact here. If the ball is caught after its first bounce, determine the resulting displacement response of the mass m. This mass m with uppercase, which is shown with uppercase m, in fact is the mass of the system, a vibrating system, with displacement or degree of freedom xt. Assume that the collision is perfectly elastic and the system is at rest initially, and we want to use these data. The mass of the vibrating system is 2 kg. The mass of the ball is 0.1. The stiffness is 100 Newton per meter. The damping constant is 5, and the height which is released, this ball is released from, is 2 meter. We know that we deal with an impact. We can use the conservation of linear momentum, and because this is an elastic impact, according to the problem description here, this is a perfectly elastic impact, so also we can use the principle of conservation of kinetic energy. So for the momentum, linear momentum, before the impact we will have the mass multiplied by its velocity, which this lowercase v sub 1 is the initial velocity of m naught, and this uppercase v sub 1 is the initial velocity of the mass m. And because this system is initially at rest, definitely this v1 is 0. But here we will not substitute 0 and we will solve it. And in the right hand side we have the second linear momentum. It's again equal to the mass multiplied by its velocity after the impact, and the mass of the system multiplied by its velocity after the impact. This v sub 2, uppercase v sub 2, in fact this is the initial condition for the vibrating system, because this is the initial velocity of this mass m after the impact, and definitely we need it to use as the initial condition. So we can write and simplify this, and also we can write the conservation of the kinetic energy similar to the example that I solved during the lecture. You can find the velocity v2 for both mass after the impact. Here you can see, if you simplify and solve it, and as I told you, the velocity, initial velocity for the mass in the vibrating system is 0 because the system is initially at rest. We can obtain the velocity of both masses after the impact as a function of v1, which this v1 is the velocity of the ball exactly at the moment before the impact. We have one ball which is released from this height h. Okay, this height is h, and we want to obtain the velocity at this moment here, when exactly a moment before the impact. The velocity here, because this ball is released and the velocity here is 0, and the velocity here is the unknown, we can easily write the energy equation between these 2 points. If we call it position 1, and this position we call it position 2. In the position 1, because this ball is released from rest, so there is no kinetic energy, and only we will have the potential energy, the gravitational potential energy, and it's equal to m multiplied by g multiplied by h. Of course, we assume that position 2 is the bottom level, or at position 2 the gravitational potential energy is 0. So by this assumption, the potential energy in position 1 is mgh. You know this method from the dynamics. I only want to remind you how to use the dynamic equations to obtain the velocity. But in the second position, in position 2, here, because we assume that this is the datum level, so the gravitational potential energy is 0, but we have the kinetic energy because we have this velocity, and the kinetic energy is equal to half times by m times by v squared. And from this equation, you can obtain that v is equal to 2 times by gh, square root of 2 times by gh, because this m will be cancelled out with this m. And finally, we can obtain that v squared is equal to 2 times by g times by h. The datum level, it's in your hand, just a reminder for you if you cannot remember that what happens here. Just to remind you that the datum level is in your hand. I mean, you can assume that, for example, datum level is here, and this distance is, for example, h1. Then in the left hand side, you will have mgh plus h1, and in the right hand side, you will have mgh1. And again, you will see that mgh1 in the left and right hand side of the equation will cancel out each other, and the final response will be the same. And again, you will extract that v is equal to x square root of 2gh. So the velocity of the ball exactly before the impact is equal to the square root of 2 times by gh here. And now we can substitute the numerical value. So we have the equation of motion, mx double dot plus cx dot plus kx is equal to 0. And as you see, we assume the impact in the initial condition. And so in the right hand side of the equation, there is no external forces, and the equation is homogeneous. The initial displacement is 0 because there is no displacement, but the initial velocity, as I told you, is v2, and v2 is equal to this term. You can substitute, and v1, the velocity of the ball before the impact, can be obtained from this term. So we can substitute, and finally we can obtain the initial velocity. And the next step, we can solve this equation in here, because I want to use the Laplace transform in this tutorial, and because the Laplace transform was the concept which was reviewed in the previous week, so I use this method. We find the Laplace transform of the equation, and here you can see for the initial condition, the initial displacement is considered 0, and the initial velocity v naught, which is in fact the v2, the velocity of the uppercase m mass. And if you simplify this, you can extract the response in the Laplace domain. As you see, the response xs in the Laplace domain is equal to this fraction. And now we need only to calculate the Laplace inverse transform for xs to find the response in the time domain. For this purpose, we should find the sub fractions c1 and c2, and the denominator will have 2 roots. As you can see, the roots of the denominator are complex conjugate numbers, 1.25 plus minus 6.9i. The imaginary part is 6.96, and the real part is 1.25. So the two subfractions are in this form, as you can see, s minus s1 and s minus s2. Now the numerator of the first fraction must multiply by the denominator of the second fraction, and the numerator of the second fraction must multiply by the denominator of the first fraction, and it must be equal to the numerator of this function, which is 1.19. So we can simplify this and extract two algebraic equations for C1 and C2. As you can see, in the left hand side, we have C1 multiplied by S plus C2 multiplied by S. This is the first equation, and it must be equal to 0 because in the right hand side we don't have any s, so the coefficient of s must be equal to 0. It means that c1 plus c2 must be equal to 0, and we can conclude that c1 is equal to minus c2. And the constant parts, I mean S1 multiplied by C1 plus S2 multiplied by C2 must be equal to 1.19, which S1 and S2 are equal to 1.25 plus minus 6.96i, two complex conjugate numbers. Now we can solve this, and from the first equation we obtained that C1 is equal to minus C2. So you can substitute here instead of C1, for example, you can substitute minus C2, or instead of C2 you can substitute minus C1 and solve and obtain two values for C1 and C2. And as you can see, C1 is equal to this value and C2 is equal to minus of this value. And when you substitute, you can obtain the xs in the form of two subfractions. And now easily we can use the table to obtain the response in the time domain by using the Laplace inverse transform. And you will see that here we have a constant number. You can factor this term as you can see here, and it will be exponential of here s1t and plus minus exponential s2t. So you can substitute, and this is the response in time domain, okay, by using the Laplace transform. Any question? Is it clear, this example, this problem? Okay. The next problem, we want to find the response of a critically damped STF system subjected to a stub force with the equation of motion as below. Assume the initial conditions as x naught is 1 and v naught is 2. So again, we will solve this equation by using the Laplace transform, because in the right hand side we have a constant value, or it's not harmonic or periodic. So the best option is using the convolution integral or Laplace transform. Of course, in the exam, I will mention that which method you should use to solve the equation. But here in this tutorial, because as I told you, because the previous concept was Laplace transform, in this tutorial I will use the Laplace transform to solve this equation. So again, we can find the Laplace transform of this equation. You know that the Laplace transform of x double dot is equal to s squared xs minus sx naught, which this is the initial displacement, minus v naught, and again v naught is the initial displacement, velocity, and they are obtained here. X naught is 1 and v naught is equal to 2. And also the Laplace transform of x dot, which is equal to sxs minus x naught, which again x naught is 1 in this problem, and plus 8 multiplied by x, which the Laplace transform of x is xs, and the Laplace transform of 5 is equal to 5 divided by s, as you can see here. So again, we can form the fraction and find the xs in the Laplace domain. You need to simplify and do some calculations and extract finally the xs, the response in the Laplace domain, which is this fraction. This fraction can be equal to c1 divided by 2s plus c2 divided by s plus 2 plus c3 divided by s plus 2 squared. Here in this case, you know that the denominator of the response, this term in fact is equal to s multiplied by s plus 2 squared, and of course we have 1 2. If you factor this 2, it will be equal to 2 multiplied by, when this 2 comes out, it will be 2s multiplied by s plus 2 squared. So you can write the subtractions in this form: c1 divided by 2s for this term, c2 divided by s plus 2, and finally c3 divided by s plus 2 squared. So in this case, you can write, and again, the numerator of the first fraction must be multiplied by the denominator of the second subfraction, denominator of the second subfraction. And for the second one, the numerator must be multiplied by the denominator of the first and third one. And finally, the numerator of the third fraction must be multiplied by the denominator of the first one. Okay, so this is the whole procedure. And now we will have three equations this time, because one equation is the coefficients of s squared, which in the right hand side is equal to 2. The second equation is the coefficient of s, which in the right hand side is 12, so it must be equal to 12. And finally, the constant part, which must be equal to the 5, which is the value in the right hand side. Now we will have three algebraic equations with three unknowns, c1, c2, and c3. And if you solve this, you can obtain that c1, c2, and c3 are equal to these values. And the next step, you can obtain the response in the time domain by using the Laplace transform. Okay, is it clear? The procedure is exactly the same, and you only need to solve this system of algebraic equations. Okay, and finally, the last problem, which is related to the numerical methods. Of course, this problem, because I just finished this concept yesterday, so you are not supposed to solve this problem in your tutorial submission. Okay, but here I will explain what is the procedure. We want to use a mathematical software to find the response of the system in problem 2 in the previous problem by using the Range-Kutta method for interval between 0 and 10 seconds, and when h is equal to 0.1 or 10 divided by 100. And we want to plot the results for both numerical and analytical methods. Of course, I solved this example in Maple code, and I think the Maple code exists on the Moodle page. I think I will check it and I can upload it. But the procedure is this, and you can use any other software to extract the mathematical code. Similar to the procedure that I explained yesterday, you can consider two new parameters x1 and x2, which x1 is equal to xt and x2 is equal to t dot or x1 dot. And now we can form two equations, two ordinary differential equations from order 1, and we can form the vector f, which vector f is the right hand side of the x1 dot and x2 dot equation. So here you can see that x1 dot is equal to x2, so this is the first component of the vector f, and x2 dot, which in fact is equal to x double dot or x1 double dot, it will be obtained from this equation, and it's equal to this term. So we can form the vector f. The initial conditions x naught and v naught are 1 and 2. You know from the previous example, the previous problem, the initial conditions were 1 and 2. Now we can calculate step by step the response. This is the response at t is equal to 0. The next step, we need to calculate the response at t is equal to 0.1, because h is equal to 0.1. For this purpose, we need to calculate k1, k2, k3, and k4. K1 is equal to h times by f at x naught and 0. H is 0.1. For f at t is equal to 0, here you can see instead of x2 we should substitute this term, which is equal to 2. You know that this is the initial condition, x1 and x2. Okay, so x2 at t is equal to 0 is equal to 2. As you can see here, we substitute 2. x1 is equal to 1. So here we will have 4 multiplied by 1, as you can see. And x2 is again 2. We substitute. And this is the vector k1. The next step, we need to calculate vector k2. The k2 is equal to, again, we need to calculate the half multiplied by k1. Here you can see this vector k1 must be multiplied by half, as you can see. So k2 is again equal to 0.1 multiplied by, this time instead of x2 we should substitute x naught plus half multiplied by k1. So in this case, you can see that x naught is 1 and 2, so it will be equal to 1 and 2 plus half multiplied by k1, which k1 is equal to 0.2 and minus 0.95. So this is equal to the next x1 and x2 that we will use this x1 and x2 to calculate k2. So this time, instead of this x2, we should substitute 2 plus half multiplied by minus 0.95, and instead of x1 we should substitute 1 plus half multiplied by 0.2. So this is to calculate k2. As you can see here, I substitute. This is for k2. For k3 we need the value of k2 again. X must be plus half of k2. Again, you can see instead of x2 we substitute the initial value for x2 plus half times by, this is the second component of k2, and this procedure will be repeated. We can calculate k2, k3, k4, and this is the x1, which is x naught, the initial value, plus 1 over 6 multiplied by this term, k1 plus 2, k2 plus 2, k3 plus k4. This is x1. And in fact, this is the response. This x1 is the response for t is equal to 0.1. And the next step, we can use it to calculate x2. This time x2 is equal to x1 plus 1 over 6 multiplied by the same term. But this time to calculate k1, you need to, instead of using the x naught, you need to use the x1. Okay, and for k2 again you will use the x1 and k1. To calculate k3 you will use k2 and x1, and finally for k4 you will use k3 and x1, and you can obtain x2. Next step, and this x2 is the response at t is equal to 0.2. And the next step, we will calculate x3, the response at t is equal to 0.3, and so on. And once we achieve to the t is equal to 10 seconds, we can stop these calculations. Okay, this is the procedure. You can use a mathematical code in any software, as I told you, Mathematica, Maple, MATLAB, or even in Excel you can use and find the response. Okay, any question from these problems? No question? This Saturday, you mean because I think the due date is Friday. Yes, you mean another one day. No, 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 no. As I told you, for the final exam or for the short test 2, we will not have problems like this, and the numerical methods only will be used in the assignment 2. Okay, in the exams we will not have like this. And for the due date of the lab reports and assignment reports, yes, we can extend another day, no problem. Any other question?
Hello, sir.
Hello, yeah. Sorry, I cannot hear you well.
How about now, sir?
How about what?
Uh, is it confirmed that our final exams will be face to face?
Final exam? The final
Yes,
exam,
sir.
you mean? The final exam, I'm discussing with LNT. I'm not sure. Maybe the final exam will be face to face and maybe it will be online. I will inform you once it was confirmed. But for now, the final exam is online. Maybe later, due to the conditions of the university and the restrictions, maybe we can convert it into face to face. I'm not sure for now. Once it was confirmed, I will inform you. I will arrange with you. Don't worry about the final exam. Okay. Yes, you can use MATLAB. As I told you, you can use any other software for assignments because when you want to write the mathematical code, maybe you have never used Maple or Mathematica, or you don't have access to this software. Any software that you have access, you can use it. Only the final response, because in the final report, you need to report the final response and you need to plot the response. In the final report, only the results are important. The software that you use is not important. Okay. Of course, you should report your mathematical code. I mean, for example, if you are using the MATLAB code, you should report your MATLAB code in your final report. Okay, I will inform you about the final exam because it's not confirmed yet, and as soon as I receive the confirmation from the LNT, I will inform you. Okay, any other question? Okay, so if you don't have any other question, we can wrap up this session. Okay, thank you for your attention and have a good weekend. Thank you.